we started the workshop with, I think, 3 basic questions that we actually gave everybody as a homework before the workshop. This time we didn't do it. I think last year we also didn't do it. We thought those questions would help people to align their thoughts a bit towards some kind of joint goal, some engineering goal. The remaining question still is, what's the future of quantum technology? If we take our focus away from quantum internet and we look at more the engineering wheel that is spinning in networks, which is all the generations of networks, 5G, 6G, and eventually 7G. My personal opinion is we are a bit late for 6G, but that does not mean we shouldn't prepare for 7G. Maybe if the panelists, Mathieu and Romain and Marco, and I think, if you could come forward and maybe share with us your thoughts on that one question that is driving us here. You can share. What's the contribution of quantum technology to next and like 6G, 7G? You can basically tune your horizon on a 10 years, I don't know, with 10 years accuracy.
So I'll start with some statements we made at the coffee break. So but this question of what's the future. So I think, in many discussions, it looks like this picture of quantum internet has been very successful in framing a direction, but maybe it's also a very remote objective if you look at the engineering and also it's not so much motivated by application if you so a possibility would be to take one step back into looking at the intermediate objectives. Like that could be maybe full service, like Holger Boche was mentioning Shor algorithm. If you distribute Shor algorithm, you can pretty much it's a well-defined problem. And then there are already papers with the resource estimate. They look at if you include a quantum memory, for example, there is a paper by Nicolas Sangois. You see how things change. So if you start to you can look at other things, but you need to have a problem that is well defined, right? Where everything is you can compute, and there are problems like this in, for example, if you want to store secrets using so what's called secret sharing and QKDs is also well defined, and you can compute everything. So I guess it's kind of more a complete service where you can use quantum technology with an advantage, and you can compute everything. Maybe it's a way to define a common goal where then you can look from different technology, how you can approach it, and then optimize what's better, how to combine things all together. So it's one way to take one step down, right? To maybe say, I want to have many bell pairs at intermediate distance, right? So conversely, this is more top-down approach. Quantum internet, or even what I said, is an application-driven, but there is like this vision that in the US have defined quantum interconnect as a interesting paper direction, also more driven by what we can do in the lab, where the technology exists, and is driven by really improving the interfacing between heterogeneous technology, increasing the dimensionality, doing the connection, and also looking at a complete set of functionality. So if you do, let's say, to do transfer a qubit to one system to another system, you need an interface. It needs to be at the correct wavelengths. You need to have a transductor. You need to look at the detector. You have to look at a complete suite of small building blocks, or still a functionality that is low level, like send one qubit to one technology to another, but that is really well defined from network viewpoint. And then, so also like look at the bottom. On the bottom is look at technology and group of technology and how to combine them to perform a small lower level functionality. So I stop here.
So maybe one last question, or not last, but so to get an idea of the time horizon, do you think we can have, say, demonstrations of technology which is made according to this thought that you brought forward in the next 10 years?
Well, for example, if you take, depends, right? It depends what you want. If you take a Shor algorithm in distributed computer, no, right? But if you say we want to do a network of distributed storage for long-term security with secret sharing and using QKD over metropolitan networks, this has been done in Japan, and we can do it in Europe. And so, yes, it depends, right? But yeah, there's a common goal maybe between those examples is that the service is well defined, and there is a metric to say, and maybe you can also do cost versus performance optimization, and then it has an impact on all the engineering, right? And you can compare engineering, let's say, directions. So, I mean, it's a different way of framing the problem than saying I want to connect Paris and Berlin and have 1 gigabit of PR pair.
Okay, I'll echo some of what Romain just said, maybe just reframing it in terms of standards. If you think about what makes the standard happen, you need a lot of stakeholders who agree that there's an ecosystem where they benefit from a common framework to make money. And I think it's not there for quantum at all right now. I think the business case for a quantum network, I think, is very weak. And it's not to say that that's not happened before. I mean, if you look at 6G, the standard, they have a lot of stuff in there that is probably not very well defined from a business perspective, and still companies are willing to look at it strategically. And so maybe we're in that phase where I think people are looking at it very strategically. Certainly international competition plays a big role. I mean, I think people are talking about sending satellites in space again from the US to do quantum in space. There's not going to be any new science done from there, but there's going to be a lot of motivation to do real cool engineering. But that's purely motivated by strategic interests on the, in the world. So I think we're still in that weird phase. So to me, it's hard to predict where the technology is going to go because it's largely motivated by how much money federal agencies are willing to pump. I don't think the investments from industry are really at scale. I mean, Google and Microsoft, of course, they're spending a lot of money, but it's not that much compared to how much money they make with all the classical services. So I think these are strategic projects, and there's a risk that we completely under-deliver, and then people say, "Oh, that was just there's just a fun distraction." So I think the roadmap, we have to be a bit careful with what we promise. I think that's kind of my general feeling. But from an engineering perspective, to me, that's exciting because there are lots of things that we can do. I made that point early in my talk 2 days ago, but I do think we're not yet at a point where we can think about quantum the way we thought about it classically. And I think we're still missing the abstractions. We're still missing the high-level reasoning that allow people to figure out whether a system will work without having to build it right away. And I think we saw that from all the experimental talks. It's super hard to make these quantum links actually work, but it's all about the timing, it's all about the stability, it's all about all these side engineering issues that are even more crucial for quantum than they are for classical. So I think, to me, when we talk about like what's the 10-year horizon for quantum technologies, it's not clear to me that will really demonstrate quantum value even within 10 years. But it's motivating us to improve a lot of side technologies, which probably will have applications beyond quantum anyway. I mean, no one will complain if they have more precise synchronization in a network, because that will allow other applications. So I think it's, in a way, to me, it feels like the moon race. People invested in sending astronauts to the moon. I don't think they accomplished much on the moon except bringing back some rocks. But I think it helped for a lot of other things. If not, popularizing, STEM, engineering and math is cool, right? You can send people to the moon. It gave a lot of money to develop other technologies that developed indirectly. I think we're a little bit there. But the one thing, and I'll finish on this, that we're missing, when people built the classical internet, they had a killer cool application they could demonstrate right away. You could send an email. Right? Like suddenly when they first did the demonstration, they were able to send a message from point A to some distant point B. And I don't think we have the equivalent of an email for quantum. I mean, we can talk about teleportation, but ultimately all we propose is demonstrating some long distance violation of Bell's inequalities. And I think that's harder to convince, for the broader public, what's the point? So we're missing the email equivalent of quantum. And maybe it's coming, and maybe I'll add one last thing, really. there's a really cool thing that I don't think we've piggybacked on enough. If you look at the detection of gravitational waves, the LIGO interferometer, they have a pre-quantum world and a post-quantum world. They suddenly activated squeezing and they gained 6 dB, I think, in precision. And that's how they started detecting gravitational waves much, much faster. And that was really a killer application that shows, yeah, you take quantum and you can deliver. But that was a sensing application. And I think that's less attractive to people who look for something flashy for quantum supremacy. So I think there's still a lot of engineering to do, but I think we're still missing that killer app, that people will say, oh yeah, I need this. And I think, Marc-Olivier, I like the talk that you gave a lot because there's something we're missing. If we could demonstrate that doing a little bit of quantum networking could add value to a general network, that would be, I think, amazing. And I don't think we even have that. Like, if you want to deploy a QKD subnetwork, how big should that subnetwork be to actually add value to the overall network? And it's a very fuzzy question to ask. I don't know how to measure it, but we're missing something that would say, yeah, a little bit of quantum goes a long way to improve some classical performance.
So, I mean, one thing I want to maybe stress is that we compare, the quantum internet with the classical internet of the idea we have with the classical internet now, right? But I mean, today, the internet does everything, but it hasn't always been like that, right? I mean, until very, very recently, phone conversation did not use the same links of the internet, right? That's an example, right? And back in the days, what was the quantum? I mean, the internet was only used by some people at university to exchange, emails or something like that. So I agree that it's very hard to start considering a quantum network for application that you don't even have and for computers that you don't even have. So I think you have to start with whatever is the current application. And the current application is QKD. I mean, I don't like QKD from what they're saying that I don't really think it solves a problem. I'm not sure how many things are hacked because people tap into the fiber, right? That's not the way you hack a network. You do it from very far away, right? You do it at IP level. So that's the security issue. I think very, very few networks have a security issue where I actually hack it by getting into the fiber, right? But I do like QKD because it's advancing the quantum field, okay, in a very practical way. Right? Now I can buy entangled photon sources. If it wasn't for QKD developing the technology, probably I couldn't do that in the lab. So I think, and that's what I like about QKD is, somehow you're building something, not maybe because you need it. You need to make a case that maybe you need it. But the idea is that you try to push it, that there is a benefit. It's like with the moon, right? I mean, the rockets were developed because now the reason why rockets are used might not be why we want it, but for sure has improved aviation and things like that, right? It's not because people are going to the moon, but the technology is being developed and used in other ways. So maybe the QKD, is developed technologies that we may not use for a QKD, but for something else. But you need to start somewhere, and I agree that, that you cannot really be the generic quantum communication network. You need to start from an application. And today we only have QKD, right? But hopefully, we need the quantum computers to start getting around. And then we'll have more application. Maybe on the quantum sensing, those could be an interesting application. And it's going to start small, it's going to start connecting a few places like the internet started. Connect only a bunch, maybe 5 or 10 nodes. And then as things got more interesting, it expanded and became what it became today. But, no one knew in the 70s what the internet would become. So I'm not sure we know today what the quantum will become. Maybe it will remain something small, right? No, we don't know.
Thanks. We also have some online participants of the panel. I don't know who wants to start, Holger or Robin?
Okay, I can start, but okay, whatever. So first, so I'm not an expert in all this quantum communication, but in quantum technology, I fully agree with what has been said. So we have to be careful not to oversell to the general public and to public funding what to promise. And so there are different pillars which are defined at the European level, international level. Quantum sensors, they work. I think that's okay. They work, but and you can buy them and they are efficient and they do what they should do. But I don't think that the big hype, whether all the money comes from public funding and even private funding, could be justified only by quantum sensor, be it gravimeter or squeezing for LIGO and so on. That would not justify the whole thing. Quantum communication has already, it's more realistic, but it's still waiting for the killer application where all the money which flows in would be justified. And quantum simulation, quantum computation is even further away. So it's a big hype. And I'm a little bit afraid that at some point the promises take too much time to be delivered, and people, including public agency, will say, okay, enough of all this, and we withdraw the big funding. Right now, quantum has a lot of funding. I know it's too much, but it's a lot of funding, and so we have a lot of people in the community, and I'm not sure if the number of new ideas and products we get is really scaling up with the money we get. And in particular, there's also now quantum is kind of a strategic topic. So every place, US, Europe, China, Australia, whatever, everyone wants to be fully independent. So we do not share as before all the knowledge which is generated, which is okay, it's really going for applications, but as long as it's not in the application level, I'm a little bit worried that at some point we overpromise. So that's one thing. So then another thing which I just wanted to add is not being an expert on the communication part, is that maybe we should not only look at the quantum advantage, but we could also do things which classical technology can do, but a more energy efficient manner. And this is already discussed a lot now. And this could be something which would justify investing in new technology. For instance, we know that now that the lasers have become much more efficient in terms of watts per photon than decades ago. So there's also energy efficiency, which is a societal issue, I think. So if you could do something which also helps to somehow mitigate energy consumption, that might also be something. It's not exactly on the quantum advantage, but I think people start to worry about this at larger scale. I don't have any product, any application where this could be a solution, but sometimes you don't need to have a quantum advantage, but an advantage on another thing, being faster, more energy efficient, something else. You don't only need a quantum advantage to be useful to the society. Okay, so that's, but I agree that I like the moon picture because, of course, we went to the moon and then we stopped going to the moon because what do we get? We get rocks from the moon. So what's the, okay, and of course, in the quantum tech, we develop a lot of engineering issues which are fantastic. It's clearly impressive progress, but so we only get the rocks back. We prove entanglement between different places, but I don't know if my neighbor will care about entanglement between even Europe and China and the US, whatever. So it's they probably will not care about this if they're not in the science community. So I think we have to be worried about this, and so we have to find a way where we can continue producing knowledge. That's important. That's what we do. But on the edge between market application and the knowledge production, we have to be careful not to burn our fuel for the science production. Okay, that's more or less what I can add to this discussion.
Okay, thanks. So I have the feeling you agree very much with Mathieu. And you already named some Teflon type of side effects. I think Teflon was invented during these efforts for going to the moon. So the sensing applications or better lasers seem to be something like Teflon. Okay, we also have Holger here. Holger, do you also want to participate?
Yes, so yeah. So if I look at the last 5 years, I think so. I'm very positive, with respect to progress. So we have. So if you, the problem is that I only know the German numbers, but somehow at the last ISIT in Ann Arbor, we also organized or you organized a workshop on on quantum communication, and we had nice discussions with our colleagues from the US, and I think they experienced the same thing. So what's the problem is, or what's the point? The point is, of course, so for instance, if I look at Bavaria, so the Bavarian state has invested 300 million euros in quantum computing and something like 4 million euros. 300 million quantum computing, 4 million euros in quantum communication. So, but if I look at the progress, what I think is that actually the most progress is achieved in quantum communication. And I'm really happy about, the progress that we see, at the Deutsche Telekom. So that's really convincing. And I have to say that, and that's exactly the problem, that most people in the public community connect quantum communication with QKD. So on a technical readiness level, so I saw the first demos, products at the Deutsche Telekom in Berlin on QKD, something like 4 years ago, and this was already a product, So if there is something like, we have something like the Bundesdruck, what's the name? Bundesdruckerei. So that's the agency who prints the money for Europe. And so if they want to have a QKD connection, just buy it. It's really on a technical readiness level that for point-to-point and for small networks, you can have it. But that's exactly the problem. Nobody wants to invest into a poor QKD system. So I think, so if you restrict the money which goes to quantum communication and not to QKD, then actually the success factor is really huge. And I think this is really nice. And maybe if we look at quantum computing, the two things that will survive in this area will be, special quantum processors that we can use in our network as network processors, the typical server, and of course the memory. And that's the thing that I saw today. That of course the Deutsche Telekom is already thinking about the memory issue. Maybe I'm too pessimistic in the quantum computing direction, and that has also something to do with my talk. But you can ask Jannis, that actually every year, in the Munich Quantum Valley, we have to answer the question, okay, please find new applications for quantum computing and how we can map the applications to, to our gate-based quantum computer. And actually the thing that we learned in this research was actually there's no compiling, no automatic, in the terms of computer science, automatic mapping. So this is really interesting. And maybe my last point, and maybe that's also interesting for Mathieu, is that I think Jannis has absolutely right that we have to connect, the wireless revolution and the wireless standards with quantum communication. And there was one remark that actually our traditional internet, we have this huge distance between application and physical communication. So actually this is not true in 6G anymore, because so actually at the moment, and at least in Europe, and also of course in China. In China, they are always open. But even in Europe, very conservative companies like Nokia or Ericsson, they're very open to, new approaches for physical layer design of wireless communication systems. So physical layer security is not an issue anymore. Latency is very important, and also dual use is very important. And I think this is one of the driving factors in this wireless world. And if we integrate much more interesting thing in the physical layer, then of course we can also map much more interesting things on a quantum communication layer. And I think there's a very natural trend into this direction.
Thanks. So we also have an audience. Do we have participants in the audience that want to shoot some questions? Okay, I have one. It's more actually. I had it this question when Dios gave his talk. So we keep saying that to match everything to the existing fiber infrastructure, but now our time horizon has say shifted a bit, right? So now we also know that there are new types of fibers, like these hollow core fibers. So the question, or one reasonable question to ask, could of course be whether these should be more considered in the research. For that, of course, it becomes then crucially important to understand how hard it is to put such a fiber in the ground. So first, when I read about this, this is very difficult. But then later I learned that at least some links have a very simple construction. You have some pipe and you blow your fiber inside there. So you can also take it out rather easily and put another one. But my question, maybe mostly to you, would be, how hard is it?
To put new fiber, I mean, well, it depends on the. So I mean, if you talk about the hollow core fiber, right? There's two problems. One is to make it. Right? There's no one make 100,000 kilometers per year of hollow core fiber. Second one is the cost. But if you could get the hand of it, I mean, Microsoft is using it, right? They bought a company who was making it. Now I think they're using it to connect their data centers. I mean, it's not even just for quantum. I mean, if you start putting hollow core fiber, it's going to improve dramatically your communication, your classical communication network, right? Straight away, you double the distance because now you have 0.1 dB per kilometer loss. You remove the nonlinearity, so you can start pushing higher power, so you can remove amplifier and locations. Problem is that as of today, you do have the amplifier, so either you run out of capacity what you have, and then you have some cost to deploy something new, and eventually you put that new fiber. I think that's the way it's going to be. Now, in terms of experiment, I mean, like for the community here that maybe goes to OFC, the conference like OFC or ECOC, there's a lot of, a lot when I say, now there is a quantum, before there wasn't. The last 2-3 years, there's a quantum committee as well, in addition to the other committees. And there's a lot of people that are doing experiments on multiplexing quantum signal on the C-band. Next to others, they're looking at the Raman effect. Where should you put your quantum signal if you have a other signal in the C-band? So there is a community that's looking at very practical implementation of this. There is maybe not so much on the theoretical quantum.
So nowadays, I learned we have every 80 kilometers roughly a fiber amplifier.
Yeah.
How is that going to change with hollow core?
Well, I mean, if you're at the moment your fiber loss is 0.2 dB per kilometer. Now the last results I've seen on hollow core fiber brings it down to 0.1 dB per kilometer. So with the same power, you can go twice the distance before your attenuation hits the level that you need an amplifier. So that's a starting point. Second thing, at the moment you're limited on how much power you can push into the fiber. Transmission-wise, because the fiber is non-linear, so like the Shannon limit doesn't go like that. It goes like this because you start creating non-linear effect. Now, if you remove the non-linearity, you can start pushing higher power, and then your amplifier has to go even further away because you reach that critical level. So I mean that's a massive. In principle, is a massive change. The only problem is that today you still have the system going. So until there is a problem with the current system, as in you run out of the capacity that you need to do another investment, no one will just put hollow core fiber when you have already the system working in the other system. You need something that prompts you to say, okay, we're running out here. What do we do next? But that's still not there, I think. But again, we will to see how long it takes as well for hollow core fiber to become commercially, quantitatively, commercially, but in quantity available. Because at the moment it's more experimental or very little produced.
Yeah.
So I think of it, I would like to maybe slightly differ from what Matthew was saying about the quantum technologies, how they will. So I see three things, right? I mean, if you look at everything happens in very slow steps. Looking back, everything happened very fast, but everything happens very slow steps first. Second, I think even if you look at the current digital sciences revolution, right? It's a convergence of technologies from different disciplines, semiconductors, communication, computing, huge convergence. Not one person can say whether all of these will fall into place. And the third thing is competition. So one of the things that really drove the classical digital sciences is the commercial application. But today the quantum has a military aspect to it, a secrecy aspect to it. The fact that somebody who develops a quantum computer can hack into my code and then possibly he can secure his communication. So the entire society may fall prey to some military intervention. So if the, I mean, in war, it's all about strategy and being ahead of the next guy, right? So it is possible that a society falls prey if they are behind in the quantum race. Somebody else does it better. China builds a quantum computer, is able to secure their communication. We are vulnerable, right? So the moment you have a competition and you have a fear that induces a human race to propel forward, so that is possibly one thing that can jumpstart the quantum race. Because here, I mean, in the classical thing, it was a commercial aspect, but here it is maybe a vulnerability aspect, a fear aspect. And I would go, I'm really surprised that you will say that you don't have that killer application. I see quantum will transform all fields of digital computing, communication, control, distributed infrastructure, everything. So I don't see any reason why somebody should not invest in quantum. It has all the killer applications. Nothing you see upfront. When Shannon wrote his paper, I mean, he never thought that we'll be communicating on wireless links. So I don't know. My perspective is that quantum is always there. It's just that if I don't do it, somebody else will do it, and then I have to do it.
I mean, I don't think I disagree, but I think BB84, I was barely born, right? So it's been around for a while, right? So I think the translation of all these ideas, which are super nice on paper, to actual systems, that's been slow, right? I mean, think about where the internet was 40 years ago and where it is today. I think it's really not evolving at the same pace. But I don't disagree. I mean, like, we develop tons of technologies, we learn a lot along the way, and that happens. But I do think we're missing the something that will convince the general public that there's an advantage. And I think it was easier to make for the classical internet. I mean, from my perspective, they are, like we are still very much, when you think about just quantum communication links, the design of transmitters, the design of receivers, we're nowhere close to doing the sort of optimization on paper, in simulation, and in practice that the folks in wireless were making, in the early 90s. And so, because they are still very fundamental questions we don't understand. I mean, you can say, use a square root measurement to design your optimal POVM for detection. Is even harder than talking about doing ML detection, right? And I think it's not like we have a roadmap or things like there are really hard thresholds to clear, which from a science perspective is awesome. I mean, I think there's no shortage of really cool problems across theoretical computer science, photonics, information theory, coding theory, and whatnot. But I do think that there's a risk we're going to have a backlash. I mean, Romain and I met 20 years ago, when QKD was, doing pretty well. And then there was a bit of a dark age, right? And quantum is coming back again, but we seem to be going through cycles. And I don't know, technology has improved a lot today. I started working on quantum because I was working on a continuous variable QKD system. And now our colleague Eleni Diamanti, I mean, these systems are now integrated on chip. They work way better. There's been tons of progress. The proofs have also evolved, but it's not like we've made this radical shift where everybody wants that system to secure their network. And I think there's a risk, but it doesn't have to be necessarily bad for us. I mean, I think we learn a lot, but we're missing the quantum email, like something that everybody wants. It's for a second. That's not going to change, right? But
It's a small email.
So
Now,
the
you can
problem
have a
is
small email with that. A short email. You can send a short email.
the problem is that no one asked for that. It's more about look what you can do. I mean, I know like in the OFC, also is the editor-in-chief for GeoCN, so I know him well. Andrew Lord from BT, he caught this idea of QKD, and he said, okay, we can buy the box, we can try to sell it. And he said, yeah, I'm trying to sell it, but I cannot actually sell it because no one wants it. And we can do stuff, but I don't think we're really solving a problem. We are being very good at selling this as a security issue because we know that once you mention security, money is poured in. And I mean, I agree on this because some things have to start somewhere, even if you don't see the application today. And I think selling with security has helped us at least moving along, because if you don't move along, you never see it. But my honest opinion is that, it's not being pushed because security is a big issue. It's being pushed because it's an excuse to do something about it. I don't really see the quantum is improving security in a way that's helpful in the next 20 or 30 years. I mean, once quantum computers are widespread, that there's enough that they start cracking all the, RSA pretty much on a daily basis, yeah, okay. Then, you get a problem. But it's very hard because no one can tell you even when a useful quantum computer is going to be available in how many years. And then the next question is that how can you do this now? How long it takes before that one gets widespread enough that you really have a security issue of that type? But that said, I'm very happy that we are pushing the security because it's helped us develop things, and maybe the quantum will evolve in a way as the internet that no one had forecast before.
Yeah, I think at the same time, people doing post-quantum crypto says that to completely implement all protocols all over the internet, it takes decades and decades. So I would not say that the problem will arise once quantum computer will start to be available, right? It will probably arise maybe 30 years before they are there. Well, I'm not so sure at all we'll have a quantum computer breaking RSA in 30 years, but the time scale is more in that direction.
So lots of interesting points. So for QKD, maybe, there is always it's always taken as an example. It's very specific because classical crypto exists, right? So it's not the same for quantum sensing, even quantum computing. You're not going to face exactly the same situation, right? So, but QKD probably has been developed not only for cryptography, but because it develops quantum networks, right? And because people were investing in the technology because it's promising to do quantum networking. So you can see it very positively as a first milestone where technology converges, everyone understands networks, we do single photon detectors. So all those things are very valuable. And for quantum information theory, we understand proofs, we understand how information leaks, how we can do randomness extraction from quantum data with information. So many things that are fundamental to quantum information theory, not only quantum cryptography. But along the path of QKD, probably a big mistake from people that try to sell QKD, in my opinion, has been to oppose computational crypto and QKD. Say either you choose one or the other, right? This has been a big mistake, and which backfires on the field at the moment, and which was from a crypto viewpoint totally wrong. Right? It's not really. Then I want to maybe slightly, or it's not disagree with Mathieu, but go. So I think in general, quantum technologies are not market driven at the moment, but it's okay, right? So maybe we pretend too much that they are and that they should be, but they are not. It's driven by innovation, by governmental and strategic investment, and so the economy. There is still an economy, a competition. It's not market driven, right? It will be maybe at some point, but maybe by saying we need a market to progress is okay. Maybe it will happen. But it's a bit there are steps before it. And to that extent, I wanted to say something else, but I forgot. So yeah.
So I watched one video on YouTube. Actually, all our group watched one video. So it's quite interesting. So right now we're trying to investigate new protocols, QKD, and also, but hackers think a bit differently. They don't care about our QKD protocols. They just send laser inside of optical fiber and read sender and receiver. Response of sender and receiver. So we can create a lot of different protocols, different like a quantum, but they constantly step forward. and we can invest millions of millions, but if our sender and receiver has a kind of response to the laser, so we can do anything, but they will be constantly step forward.
I mean, there is a whole aspect of QKD, which is certification, right? And so really to not only to operate the system, but to operate against hacking, right? And so and to really field test the systems, to make a separate evaluation labs that are private. I think Dutch Telecom has one, in France there are a few, right? So do the job of really, this is done in classical cryptography. This is also, I think it's a very interesting topic also scientifically for quantum cryptography, how to do it. It's different, right? You have different challenges. But I mean, this is taken in the roadmap. But we know we have to do that to do practical quantum crypto in the field, and this is being addressed. Right?
So maybe if we have 5 panelists, if each of you could try to say put forward his favorite focus point that we should focus on in the coming years, that could probably make a good conclusion.
Have one. So yeah, so because to move away from QKD, even in these pictures that I showed in my talk, there now we have in the world we have short-term quantum memory, and so maybe we could rephrase an important application, or I mean something that is worth really focusing efforts on that we can do with that technology, right? So I mean we don't have long-term quantum memory, we have short-term quantum memory. What do we want? Maybe try to agree what is important to do, valuable to spend efforts on, and then again do the work of putting technology in competition, optimizing protocols, and understanding the theory, what is possible, impossible. I think maybe we are too much focusing on this long-term vision that we want to have again long distance, a lot of long distance EPR pair in long-term quantum memory, but there are things to be done before. Yeah.
No, I like what Romain said a lot, and so I'm going to add to that. For me, when I take that and I, narrow it down to my concrete interest, there is absolutely amazing work to be done on receiver design. Take a photonic system, you send these flying qubits. How do you actually, design a protocol that uses them properly? Just say even if you just want to do something as simple with quotes as achieving the whole level capacity. So not even quantum, but classical communication over quantum channels. You encode that in photons, how to do that effectively, how to translate the information theoretic results in something you can concretely build in the lab. And memories are going to play a role, right? Because right now we can design crazy things with memories, but they don't quite exist. But maybe memories with some constraints, we understand their lifetime a bit better. Maybe we can start designing things that will really pave the way to these, general receivers. We're nowhere close to having like a match filter that we know will solve every communication problem, like in the classical world. But I think there's a lot we could do by maybe trying to look at where the technology is today, where it's going in the shorter term, that will drive a lot of innovation. And there's a lot of work to be done to think about transduction, right? I mean, how do we go, even at the theoretical level, between flying qubits and stationary qubits, that you go from photons to atoms, like all of these things will give you constraints, and there's a lot to be done on the protocol design. That, to me, from a more theoretical perspective, is super exciting.
So, I mean, if we talk about the networking aspect, I mean, to me is how do you implement a quantum network that goes beyond one link? That implies, I mean, the work that I was discussing, for sure, how do you use it at least in current dark fiber network? Okay, forget about multiplexing with WDM, right? Just how do you use it there in a way that you can actually use the switching, so you don't just call link, but you might say around. And more importantly, all the protocols that goes behind that, right? So quantum network is really an entanglement distribution network, which you do teleportation because of the loss. And what are the protocols that actually makes that work from a network perspective? But overall, I think what's already happening is that you really need a quantum computer that's doing something useful. Something properly useful that say, okay, there is a really strong business case to start driving seriously what's behind from a commercial perspective. The moment this is driven from an interest perspective, academic industry also, a lot of industry comes out of personal interest. But I think, if you really want to if you really want to say, okay, now you need to scale it up, you kind of have to demonstrate that quantum computing is actually doing something that's valuable commercially.
Okay, we should move on to maybe to Robin.
Yeah, so maybe as a wrap up, yeah, I would say, given what we all seem to agree on the readiness level of the quantum tech, I would say that we should maybe try to use the support we have of the public investment and so on to make more connections between different fields of research we have, which start to be connected, be it from theoretical physics, communication, information science, to hardware things. I think that's good. And as an example, I want to give the independent computing context. Like 20 years ago, there were ions and superconducting qubits, which were like the promising stars. And very recently, someone came with an experiment, a new device, Rydberg atoms, and then suddenly the whole thing flips. And so maybe we'll have, if we still try to be on the conceptual and research level, maybe find new systems, and someone will come up with a new device or new concept or new protocol, which would be more creative than pushing the engineering of the existing things we have so far. So I would push or let's say favor and incite people to go across their community to see what kind of input they can get, and tries also to invest, if you are sitting on panels, which some of you might be, try to support things which are a little bit not more of the same, but a little bit different type of exploring system. So I sometimes give the example that because most of the funding goes to the big groups on the big platforms. And for me, it is a little bit like if you look at soccer, football. So if you only have the first league and all the money goes in the first league, and you have no second league and third league, you will never be able to get all the community and get the new people coming up. So you need to invest also in second league and third league. And so if in the panels where we are sitting, we only give all the money to more of the same in the big players, I think that would be not good. So we should also support and sustain the research at a lower level below the radar. And in particular, I'm very in favor to connect people from different communities. If there's anything creative, which is even a little bit crazy and with less success probability, but creative, I'm pushing this type of projects a lot. Okay, that's what I want to add to this.
Many thanks. Holger?
Yeah, I think so. Historically, it was a huge mistake to separate communication and encryption. Yeah, that was a huge mistake. But at this time, when they did this decision, there was no chance to do both things at the same time. So as I mentioned today, even in 6G, we have this latency problems, but also dual use, dual use in military. They like the idea of physical layer security. So I think this is a very promising thing. We should do this in a classical setting. And then, of course, we have to bring together these two communities, the classical cryptography and the communication engineering. And I think that's a very challenging task. So Mathieu, of course, wrote his book on physical layer security a long time ago. It had a huge impact in the whole communication engineering and information theory community, but on the cryptography side, the impact was very limited, I would say. And we still have to remember. So I was 1992. I was at the Bell Labs, and actually even at the Bell Labs, Shor's paper was a huge surprise because most of the people at Bell Labs thought that factoring integers on quantum computer is a very hard task. So that was a big surprise. And I have to say that, of course, post-quantum crypto is it's only a selling. It's a selling concept. So everything that we know, for which we at the moment know that there's no quantum algorithm, is post-quantum crypto. But maybe we will find so. As I want to say, Shor was really a huge surprise for the whole community. So that's a thing. And then somebody mentioned the point that we should do with quantum, not the things that we can solve classically. So that's very important. So that's why I like, all these things, new protocols, oblivious transfer, interactive local games. I think, manipulating behavior network, for all these things, for new jamming, for new types of services, applications, we should also use the power of entanglement. And we know, for instance, for jamming, we know that the only strategy for encoder-decoder coordination to move any jamming strategy into a noise strategy is entanglement. So with classical resource, that's not possible. Entanglement is the only resource. That's also, of course, very important for dual use applications, but it's also very interesting for operators and for attacks on networks of operators. So I think we should look for these type of applications to use the full power of entanglement.
Okay, then thanks to all the panelists and to all the remaining attendees.